Good day, everybody. I will speak today on congestion games with a loss criteria. This is a joint work with my two co-authors, Babacar Tour and Simon Paturel. It is based on homework in my 6 hours BSc course in Supelec, in which the students make their first steps in research. Here are assumptions that one often finds in frameworks studied in the literature. The cost is additive. By that I mean that the cost over a path is the sum of costs over the links along this path. Examples are delay and tolls. Another assumption is that flow is conserved. By that I mean that all flows that come into a node also leave the node. There are several ways to classify routing games. One is according to whether they are atomic or not, and the other way is according to whether they are splittable or not. A game is called non-atomic if each player is infinitesimally small. By that I mean that it has a negligible impact on the performance of other players. A game is called non-splittable if there is a constraint that each player should send all its traffic through one path. An example of a framework that satisfies this assumption is that by Rosenthal, who further assumes that all flows have equal size. In that case, it turns out that this is a potential game. There is a potential function, and its maximum gives the equilibrium to the original problem. In this work, we did not make the above assumptions, and therefore it turned out that the game is not a potential game, which is the challenge in studying this framework. Here is our network, which we studied in this work. It contains 3 nodes, S1, S2, and D. There are 2 n players, each of which is identified with a flow that is associated with that player. Each player controls the route of the flow by all packets of the flow. There are 2 sets of such packets, N1 and N2, each containing n flows originating at each one of the source nodes Si, where I is 1 or 2. We shall denote by the couple N and I, player N among the capital Ni that is connected to source I. D is a destination node that is common to all 2n players. Each flow can choose 2 possible routes, which are the 2 possible actions. Direct path, or DP, and indirect one, which is IP. The DP, the direct path for a flow arriving at Si, is the link Li, which is defined to be the one between Si and the destination node D. The indirect path has 2 hops. A bidirectional relay R from Si to Sj, and then the link Lj from Sj to the destination D. So these are the 2 actions, the direct path or the indirect path. We consider in this work 2 types of objects. One is packets, and one is flows. The interaction between all players occur at the packet level, since packets of different flows may collide. but decisions are on a flow level. A player is represented by a flow, whose cost is the average losses in the packet level. Now the loss model. We assume IID losses on the relay channel. In other words, a packet originating from a node Si and related to node Sj is lost with probability Q there. We further have collision losses on the links Li. Whenever an arrival occurs where there is another one in service, then there is a loss. The transmission duration of a packet in link Li is assumed to be exponentially distributed with parameter mu. Now, the total flow sent to the link Li consists of the superposition of first the Poisson flows that arrive at node Si and are transmitted over Li, and secondly, the Poisson flow originating in node Sj, consisting of the packets that were not lost in the relay to node I. A policy is a map U from the two n-player set to the two actions of each player, dp and ip. Due to symmetry arguments, we shall work with simpler objects to describe policies. So instead of these high-dimension objects, we can write alpha iu as denoting the sum or the fraction of players among Ni that choose dp under policy U. The loss probability experienced by a player, Ni, depends on the actions UMI of all other players only through their sum or through the fraction alpha iu. We shall call alpha multipolicy. We say that a policy U is symmetric if alpha I of U equals alpha j of U, and then we denote the scalar by alpha. To compute the loss probabilities, we use the fact that a Poisson process with rate L, which is thinned by randomly dropping points with probability Q independently, is also a Poisson process with rate which is the product of L and 1 minus Q. Secondly, we use the fact that a superposition of independent Poisson processes is also a Poisson process, and its rate is the sum of the rates of the two processes. Under a symmetric policy alpha, the total rate of arrivals to Li is given by the following equation 1. This has two terms, one corresponding to n Poisson flows that take the direct link, and one of n other Poisson processes that take the indirect link. The probability of a packet to take a direct link is alpha, and the probability of taking the indirect link is 1 minus alpha. We thus have the superposition of two sets of Poisson processes. The first n that's in direct traffic and is thus thinned with parameter 1 minus alpha, and the second set which is thinned with parameter alpha. In the second set of Poisson process, we further have thinning with the parameter Q, which corresponds to the IID losses on the relay. We conclude that the loss probability of packets at Li is R alpha divided by the sum of R alpha and mu. Under symmetric policy U, the probability of losing packet on the direct link is also the probability of losing the packet on the direct path, because the direct link is the direct path. But now if the player routes the flow through the indirect path, then the loss probability is a little more complex, and you see it in the last equation in this slide. So it is either to lose the packets on the relay channel, or if it is not lost on the relay channel, then the probability to lose it on the direct link from source J to the destination. We shall next compute the global loss probability. It is composed of three terms. The first corresponds to the direct path. The second corresponds to the link on the indirect path between the source and destination, and the last term corresponds to the relay channel. We apply this result for optimizing globally the system, or in other words, for minimizing the loss probability in the system. We differentiate the loss probability with respect to alpha and obtain the following expression that you can see on the bottom of the screen. This expression turns out to be negative everywhere, and this implies that P alpha decreases in alpha and is thus minimized at alpha equal 1. Next, we consider the competitive case. So we're looking for conditions on the Nash equilibrium. U turns out to be a Nash equilibrium if and only if the following two conditions hold. The first is that any player that chose a direct path does not gain by deviating unilaterally to the indirect path. And the second is the converse, that says any player that chose an indirect path does not gain by deviating unilaterally to the direct one. Now it turns out that if the problem has a symmetry, and we have also symmetrical equilibria then, and in that case we don't have to check the two conditions. The first one always is satisfied. So any player that chose direct path doesn't gain by deviating unilaterally to an indirect one. And therefore the second condition turns out to be sufficient and necessary for the policy to be in equilibrium. We show in the next slide that you can never gain by deviating from dp to ip. And therefore there is in fact only one condition that has to be satisfied. A player that deviates from direct path to indirect path has as a result its rate of packets change from the expression we had before in 1 to the expression in equation 3. And this implies that the loss probabilities for this player is the expression in the end of this slide. A simple calculation shows that when a player deviates from direct path to indirect path, then his loss probability does not decrease. Therefore, it suffices to check if a policy is in equilibrium by looking whether a deviation from IP to DP can be profitable. Now, this brings us to the first result. The symmetric policy that sends DP by all players is in equilibrium. And this holds for any parameters mu and q. We shall next show that, in fact, there may be several equilibria depending on the parameters of the problem. So choose some symmetric policy alpha, and let there be a player that deviates from indirect path to a direct one. Before the deviation, his lot rate is given by p tilde, the expression that you see in the first equation, and after deviation it is p bar. Here are some observations on the properties of the equilibria. First of all, let Q be positive and fix the value of mu. Then there exists some n0, such that for all n larger than n0, all symmetric policies alpha greater than or equal to 0 are equilibria. So this follows from the fact that as n grows, the argument of z in equation 4 above tends to 1 minus 1 over q, and this is negative. So it is a direct consequence of the fact that it is negative. Next, fix n and mu. Then for all q sufficiently small, the globally optimal policy is the unique equilibrium. This follows from the fact that as q vanishes, the argument of z tends to infinity. And that is because the leading term there is 1 over nq squared. Here are some more properties of the equilibria as a function of n. We see in the argument of z there are 5 terms, and in fact only the last 3 depends on n. So we observe these terms and get the following. If q times mu plus 1 is greater than 1, then alpha star is increasing an integer concave in n. Thus the number of equilibria increases in n. If the converse inequality holds, then it is decreasing an integer convex in n. The number of equilibria decreases in n in that case. Let's finish with a numerical example. In this figure, figure 2, we show delta as a function of alpha for fixed n and mu, n equals 10 and mu equals 1, and for 4 different values of q. For q equals 0.1, delta is negative for all alpha. Thus there is no equilibrium other than the trivial one, alpha equals 1. This was a result for a large value of q. On the other extreme, for q small, so in that case q equals 0.003, all positive alpha, which are multiples of 1 over n, are symmetric equilibria, as delta is seen to be positive for all alpha. For q equals 0.05, delta is positive for all alpha greater than or equal to 0.9, and are negative for other integer multiples of 1 over n. Thus only 0.9 and 1 are symmetric equilibria. We note directly from equation 4 that if for some n, q, and mu, alpha is equilibrium, then also any other alpha prime smaller than alpha is an equilibrium. For q equals 0.05, delta is positive for all alpha greater than or equal to 0.9, and are negative for other integer multiples of 1 over n. Thus only 0.9 and 1 are symmetric equilibria. We note directly from equation 4 that if for some n, q, and mu, alpha is equilibrium, then also any other alpha prime smaller than alpha is an equilibrium. Here are some conclusions. We have here a Cometa-type paradox. The paradox in our way is that a lower random loss parameter q, and thus a better channel, causes at some equilibria a higher use of the relay channel and hence a worse performance at equilibrium. This is similar to the brace paradox, except that brace paradox has another topology. Cometa paradox has the same topology as we have here, but he deals with delay functions and not with loss functions. We turn out not to have a brace paradox for the best equilibrium, for which we showed that the price of stability is 1. Yet the paradox does appear for other equilibria. Thanks.